Hi all, let's see the next topic of Unit 3, the floating point addition and subtraction operation. So in today's lecture, we are going to discuss about an introduction to floating point addition and subtraction and hardware implementation. So coming to a floating point numbers, we have already discussed about a floating point representation. So in the floating point number in the computer register, it mainly consists of two parts. The first part is said to be called as your mantissa, and the second part is nothing but your exponent. And we also have something which is called as a base. So it is represented in the form of m into r to the power of e, where m represents your mantissa part of your data, and r is nothing but your base or radix, and e represents the exponent. So we can represent a floating point number in the form of m into r to the power of e. So let's see an example of a floating point representation. So if you consider the 9 into 10 to the power of 8, so 9 is nothing but your mantissa part of your data, and 10 is your base or a radix, and 8 represents your exponent. Similarly, if you consider 110 into 2 to the power of 7. So since this is in a binary form, we are representing it to the base of 2. So the mantissa is 110, whereas your base is 2 and the exponent is 7. Similarly, if you consider this 4364.784 into 10 to the power of minus 3, in this particular representation, the entire 4364785, this entire thing represents your mantissa part of your data. Whereas your 10 is your radix or base and minus 3 represents your exponent. So these are the different examples of a floating point representations. Now let us see the hardware implementation of floating point addition and subtraction operations. For this is the hardware implementation for all the floating point arithmetic operations. So the same hardware can be implemented by addition, subtraction, multiplication, as well as the division operation. It is a common hardware which can be implemented for all the floating point arithmetic operations. So if you look at the hardware of this floating point arithmetic, it is just similar to your fixed point arithmetic operation. The same registers are used here in case of a floating point operations also. So we have three registers: AC, BR and QR registers. And the difference between the floating point arithmetic and the fixed point arithmetic operations is that in case of a hardware implementation, in case of floating point numbers, we need to also deal with the exponent part of your data. So rather than having AC, BR and QR registers, we also have three more registers called small a, B and Q in a smaller case. So the registers are divided into two parts where half of part of your register is represented in the form of your uppercase letters B, A and Q, and these are used to store your mantissa part of your data. Whereas the smaller case letters registers which are represented by a smaller case small a, B and Q, these are used to store your exponent part of your data. So AC is divided into two parts, capital A and small a, where capital A stores your mantissa part of your data, whereas small a stores your exponent part of your data. So the way similarly for all the registers that are present in the hardware. So similarly, when we have a parallel adder similar to a fixed point representation, it is used to add the contents of BR register and AC register, and the result is stored back into the AC register. And we have a flip-flop E that is used to store our carry bit during the addition operation. The A1 AS represents the sign bit, whereas A1 represents the most significant bit of the contents of AC register. So if you look at the QR register, it contains a sign bit. So we are dealing with a floating point data. So here the sign bit lies together along with your data part. So in order to perform an arithmetic operations on the contents of capital A, Q, and R, we are using a parallel adder. Similarly, at the exponent side also we have to perform an arithmetic operations. So for that we have a parallel adder and a comparator, which is used to compare the exponents and perform an addition operation on the contents of any two exponent part of your data. So So the register configuration for a floating point operation, it is very similar to a fixed point operation, because the same registers and the same parallel adder that is also used for a floating point hardware in a floating point hardware. The only difference which is lies in the way the exponents are being handled in the hardware. So we have three registers: AC, BR, and QR. So each and every register is subdivided into two parts. So the mantissa part, has the same uppercase letters. The exponent part is stored in the corresponding lowercase letters. And we also have a parallel adder which is used to add the two mantissas and transfer the sum into A and the carry bit into E flip flop. Similarly, for the execution part of your data, we have a separate comparator and a parallel adder that is used for you to perform an arithmetic operations on your exponents of your floating point numbers. So this is about the hardware implementation of floating point addition and subtraction. Thank you.